Hey students, this is our notebook for Investigation 6, and it's all about volcanoes and earthquakes. So let's check it out. Oh, typo. 6. All right, we're learning to hypothesize that earthquakes and volcanoes occur along plate boundaries. We're learning to identify that Earth's crust and solid upper mantle make up the lithosphere plates. We're learning to explain how the plates float on top of a semi-solid layer of the Earth called the asthenosphere, which I like to call chunky molten jello. And we're learning to describe the effects of plate movement, including volcanism, earthquakes, and continental drift. And why is it important? Well, in this investigation, we explore where volcanoes and earthquakes occur on Earth. Are there any patterns that we can study about where they happen? How can we avoid risks and loss of property and life? When we start to understand where volcanoes and earthquakes occur, we learn that much of what is on the surface of the Earth is shaped by processes going on inside it. We are putting the puzzle pieces together to better understand the amazing planet that we call home. And we will have a rock cycle modeling project in 2 weeks, which will be our final project. So the first part of this notebook is about volcanoes. So prediction, where do volcanoes and earthquakes occur on Earth? So you fill in your prediction. Where do you think they happen? Where have you heard about them occurring? In what places? What types of places? Fill in your prediction there. And then we did this in class for remote and for in-person students. So what I would do is I would just click on the map for your class. I think I would avoid period 1's map because we got kind of stuck in the weeds with Google Map. And for the rest of my classes, I used Google Earth, which worked much better. So check that out. Check out 3, 4, 5, 6, or the remote class. I'm going to go period 4 and look at the data that they plotted in Google Earth. Everybody worked together to put these volcanoes into the map, and we shared our maps, which is nice. Of course, it loads very slowly. So where do volcanoes occur? I'm seeing a lot along coastlines, or in the water, or on islands. I'm seeing a lot around the Pacific Ocean, the Philippines, Japan, Russia, Alaska, and of course the Pacific coastline, Washington State, California, and Hawaii. And then if I travel down, still along the Pacific Ocean, I see quite a few are along the South American coastline. And so I would say, where do they occur? Definitely around the Pacific Ocean. Often along coastlines or on islands. This wanted you to look at a particular volcano, so Control-C, Control-V that into Google Earth. So you could go to your search bar, Control-C, Control-V, and take a look at that one. And see if you can figure out what volcano that is and what is the importance of that volcano or the history of that volcano. Take a look. It's amazing. You're going to skip this part, but you can answer this question. What patterns do you notice? And then taking a screenshot of the map. I would take a screenshot of the map in a location that looks particularly full of these yellow dots, because these yellow dots are volcanoes. All these pinpoints are pinpoints that your class has mapped. So I would probably take a screenshot of something like right around here, because it shows that there are a ton of volcanoes around the Pacific Ocean. So I would Control-Shift and then do my little screenshot button to grab a screenshot of that and insert it here. Earthquake patterns, go to the USGS Live earthquake data site. This is pretty amazing. So if you zoom in a little, oh no, it just takes a little moment to load. So this is pretty live data for earthquakes happening on Earth. You'll notice the date is always whatever day you're looking at it. So there's been a lot of earthquakes today. Hawaii, California, Alaska, California, Oregon, Hawaii, California, Hawaii, Alaska, Oregon. Are many of these same locations places where there are volcanoes? Yes. There are not as many volcanoes down in some of these parts of California. There are volcanoes in these other places that we're seeing. So thinking in my mind, volcanoes and earthquakes often are happening in the same locations. I wonder why. Most of these are pretty small, but this 4.9 is a decent size. It ranges from 0 to 10. It's called the magnitude of an earthquake. And most of these are small, and so small that probably people didn't even feel them happening. It needs to get to around a magnitude of 3 in order for people to feel it. So most of these people did not feel. So you have to look and see what was the most recent earthquake with a magnitude of 4.5 or higher and where did it happen, and fill that in. How do the earthquake locations correspond to the red lines? Let's look again. What do these red lines seem to have in common with the earthquakes? How do they correspond? Seems like they correspond pretty well, especially when the dots go away. I can see that these dots are happening all along the lines. What are those lines? What do you think? Take a guess. Is there a connection between the earthquake patterns you see and the volcano patterns? Fill that in. And there's a pattern of volcanoes and earthquakes around the Pacific Ocean. What is it called? Some of you probably know this, but some maybe don't. The pattern of volcanoes and earthquakes around the Pacific has a cool name, a fiery name. It's called the Ring of Fire. And why do you think it's called that? Well, volcanoes maybe? Yeah. So there's lots of volcanoes along this area, and what it is, it's the Pacific Plate is this whole crustal plate under the ocean. So there's one giant plate, lithosphere plate, made of crust in the upper mantle, and it's under the ocean. And what you're seeing is out along the edge of the Pacific Plate, volcanoes and earthquakes are happening all along the edge of the Pacific Plate. Oh, isn't it convenient that we happen to live along the edge of the Pacific Plate? I think so, because I think it's cool that we have volcanoes and earthquakes here. But sometimes it has not been cool historically. Mount St. Helens was enormously devastating, and people died. I think it was 56 or 57 people died. It was the most devastating eruption in recorded history. It dumped ash all over the state of Washington and all over the country. Check out this video about it to give you some historical background. And then for the next 3 definitions, it's different types of volcanoes. So what you'll do is you will, if you know, you could write what you know about these 3 types: active, dormant, and extinct. Or you could use the Earth History Glossary to fill in the definitions. And then for these types of volcanoes, you're going to use the volcano slide to fill in those. So shield volcano, and if you click on it, it gives you more info. See this gently sloping broad mountain? This would be a Hawaiian volcano, Mauna Kea. When these erupt, they don't erupt like Mount St. Helens. The lava here is mostly basalt, and it flows more gently. It doesn't plug up and then explode, blasting giant holes in the mountain like Mount St. Helens did. And that's because Mount St. Helens and all of our volcanoes here along our coastline are called stratovolcanoes. So this is Mount Rainier. It's a stratovolcano. It's made of layers of ash and sticky lava. And because it's got like sticky, chunky layers, the lava does not flow. The lava itself is sticky and chunky and does not flow gently. It plugs up, and that causes a lot of pressure inside. So when they erupt, they can erupt violently, like Mount Vesuvius, which was the first volcano example from above that destroyed Pompeii. So there have been some very devastating stratovolcano eruptions in history. And then cinder cone was on there too, so you can fill those in. Okay, Alfred Wegener. This was a guy who was a German, and he was a meteorologist, so he studied the weather, but he was just a lover of science, so he also studied maps and geology, and he came up with a theory for continental drift. Before his time, people did not know that the continents moved around at all from their current locations. They thought they were sort of fixed. And so he came up with a theory for Pangaea, that the continents had once been connected, and he looked at all this evidence for his theory. So check out this video and then fill in what was his evidence that he used to support his theory, and what did other scientists say about him. Spoiler alert, they did not think that he was a very bright guy. So fill in an idea for that. And then listen for how did other scientists explain why the continents seem to fit together. So pause the video for those 3 questions. Pause this video, watch this video, and answer those 3 questions. And then for these remaining 2 questions, a plate. I would probably, for this, I would say a plate is a solid slab of lithosphere made of the crust and upper mantle. A solid slab of lithosphere made of the crust and upper mantle. And the theory of plate tectonics, I would say, well, tectonics means movement. So the theory is that the plates have moved over time. That's the basic theory. The plates have moved over time. Okay, Pangaea Puzzle gives you a chance to use the evidence that Wegener used to come up with his theory for Pangaea. So click on that. And you're going to look at the continents and see if you can piece them together in a similar way that he did. So if you watched the video, you know that he started really kind of by looking at Africa and South America, because he noticed that the shape of those continents fit together like puzzle pieces. So if you're going to start putting this together, you should start with them. And then you're going to have to look at the fossils, right? So some plants, there's the Mesosaurus. See if you can match up some of these yellow and blue fossils. And then you're going to take a screenshot of your Pangaea and insert it into your doc. Remember, when you take a screenshot, it's Control-Shift, and then the little square with the little brackets. It's above the 6, I think. That's your screenshot key. And then you draw like a little rectangle around the thing you want to take a screenshot of, like this. And for you, you'll be able to just copy it to your clipboard and paste it into your document. So click on the button that says Copy to Clipboard, and then you can just Control-V, put it in here. What causes the plates to move? Why do you think that is? Take a guess if you don't know. This is not exactly related, even though it's really cool. If you have time, check it out. But otherwise, just think about what you think causes the plates to move. And we'll kind of go over what's going on with the plates next. So for these, we're going to fill in the type of layer and what its consistency is. So the top layer is the outermost layer that they want us to fill in. It's oceanic crust. It's a solid rock. Okay, it's crust made of basalt, solid rock. It's an igneous rock. And it's a dense rock. Basalt is dense. It's a very, what does dense mean? It has a lot of mass for its volume. So if you were holding it in your hand, even if you were holding two rocks that were the same size, if one of them was basalt, it would feel heavier because it is denser than the other rock. Layer 2 would be continental crust, which doesn't really fit. So I'm going to make it a little smaller. Continental crust is also solid. It's also made of igneous rocks, but it's made of granite, and it's sometimes made of sedimentary rocks too. These are less dense than the oceanic crust, and that's going to matter when we start to learn about why volcanoes form. Okay, it's not letting me scroll down, so I'm going to zoom out. Underneath continental crust is the upper mantle. The upper mantle is also a solid, and this is a very dense solid. It is got iron, magnesium, so it's more metallic. It's also super hot down there because you're getting closer to the core, which is fiery hot. The actual core is as hot as the sun. Whoa. I have to zoom out so much to be able to access that. That's annoying. Once I click on it, let me see if I can zoom in and it will let me go to that spot. No. Well, I can get down here. Under the upper mantle is the asthenosphere. Nothing related to Thanos, actually. I'm going to make it really small for it to fit. Asthenosphere. It is the chunky molten jello I keep talking to you about. It is semi-solid. What does that mean? It's not a liquid. It's not a solid. It's like oobleck. A lot of people talk about oobleck. It kind of flows like a liquid, but it has other behaviors of a solid. And I think it's a semi-solid too because it's got so much like sort of magma, hot, molten material. It really can flow, but it's also got a lot of pressure, so that makes it partially a solid and partially a liquid. And it is going to be underneath the solid plates. So the plates are made of the crust and the upper mantle. Well, what's underneath the plates is this chunky molten jello flowing material. Think about jello, it's kind of jiggly wiggly, but if it was full of like chunky material and it was really hot, that's kind of what this would be like. And so, yeah, the plates are on top of that. We're on top of that. So think about it. You think we stay still being on top of chunky molten jello? No, we don't stay still. We're moving around, right? The plates are moving around too. Underneath the asthenosphere is the outer core. This fits barely if you make that box a little bigger. And then the inner core. And what is there to notice about the outer core and the inner core? The outer core is made of iron and nickel. metallic metals. It's so hot. Look at the temperature. And it's very dense because there's a lot of pressure. And the outer core is a liquid, and the inner core is a solid. And I don't know how they know that. They say that they use earthquake data, but I don't know how they figure that out. It's interesting to me though. Okay, so then save and close. Okay, sorry. And that should do it for you for that. So think about this now. The plates are floating on chunky molten jello, and inside that chunky molten jello, you get these currents. They're called convection currents. Here's a video of convection happening. So think about how you would have inside the Earth heat from the core. So here's a heat source. Heat from inside that's going to be flowing through this chunky molten jello material. It creates this thing called a convection current, which sort of cycles like this. So you're going to start to see the convection current happening in this basin. You see cold at the top, which would represent like the surface of the Earth, where it's cool. It's relatively cool up here, comfortable temp. It's cooler at the top, but inside the Earth it's super hot. So what is happening? Well, you have hot material. Hot material is less dense, and it is getting pushed up and out of the way by cooler material because as it rises, it cools down. Now it's going to sink again. Then it's going to heat up by the core and rise up, and then the cold material is going to cool off. The material will cool off, and so then it will become more dense and it will sink again. It will become hot by the core, and it will become less dense and will get pushed up and out of the way. Then it will cool down and sink. Okay, so it creates these convection cycles inside that chunky molten jello. So what should we say for what is convection? We could say the movement of heat through a material in which the cooler material sinks because it is more dense, and the warm material is pushed up because it's sort of pushed out of the way. And so you could say it rises or it's pushed up, and that creates a cycle. Or something like that. Or you could Google it. How does convection play a role in causing the plates move? How do you think? Okay, here's a good picture of it. How do you think these convection currents are playing a role in the plate movement, which you see happening up here at the surface? Okay, this is our final step we're going to need to finish in our notebook. And it's different types of plate boundaries. So you can show me with your hands, and I actually didn't have people put in the diagrams because we were running out of time. But what happens on a divergent plate boundary? The plates are spreading apart. They're moving apart. So the plates move apart. What happens at a convergent plate boundary? The plates are sliding together. Sometimes maybe they will push up. Sometimes one will go under if it's denser. But in general, converging means coming together. What happens at a transform boundary? This would be when one plate sort of slides past the other plate. A subduction zone is a very fancy convergent boundary because you have an oceanic plate, which is denser, remember it's basalt, sliding under continental plate. So one goes under, and then what happens is this movement melts rock and forms magma, which has to go somewhere, so it erupts out. So subduction zones are where one plate is sliding under the other plate, and it forms magma chamber in a volcano. And now a spreading ridge is just where in the ocean two plates are going apart, two oceanic plates are moving apart. And what happens in that gap? Magma and lava are coming up and filling in that gap and forming new oceanic crust. Okay? So there are some other good video links in here if you have time. You could also challenge yourself and compete against your classmates with this Kahoot. Otherwise, just submit on Schoology and you're good to go. Okay, send me an email if you need any help.